All right, folks, thanks for coming to the system seminar today. And today, I have the pleasure to introduce the work of Ivan. You can be there? Mhm. Yeah, it's Izhbirdeev. And actually, I never pronounce your name. Ivan is actually just 1 year old academically in my group. He started his PhD in spring of last year. It's been I actually met him back in 2018. He was a student in my 350 class. Then he came here back for a master, and now he's a PhD student. But what's very interesting is that this is his first publication as a PhD student, was a first author in my group. And this work was accepted at this year, was presented in December, this year's RTSS, and received the Best Paper Award in the absolutely topmost competitive conference in our field. So that must mean something. So today was the Ivan has for you is essentially a software hardware technique to be able to control the memory consumption extracted by application running on application cores. And the name of the technique is called MemCoRe. So get ready for a little bit of software, a little bit of hardware, a little bit of OS, a little bit of everything. But without further ado, I'll let Ivan get started with his talk. Thanks a lot.
Questions in the middle, or would you like?
You can ask questions anytime, and there have a little email. Yeah, it's give it a question, given the small one. Thank you for the introduction.
Of course.
Okay, so I'll present you our system for regulated memory bandwidth. As another set we call MemCoRe, and it stands for Coherence-Aided Memory Bandwidth Regulation. So first, let's talk about our modulation. So shared memory is a known source of temporal interference. So what it means that completely logically independent cores can affect each other's performance. Thus, it makes the worst case execution time analysis very pessimistic and the overall system much less predictable. And with increased interest in a multi-core system nowadays, dealing with temporal interference like this becomes a very important subject in real-time systems research. So before we start, let me demonstrate and emphasize this with a example. So assume you have a periodic workload on a single core in isolation. So we have the core, right? We have the wall clock deadline, and we have the task period and deadline. They're going to be the same. So now let's run the work, and it runs fine. So it finishes in time. Now let's add one more logically independent core with another periodic workload and see what happens. So now we see jobs on core 0 also finished in time. However, now it takes longer. And the reason for this is because workloads in both of these cores access shared memory, which among other things results in contention on the bus in the memory controller. Therefore, the same task can take longer time to finish. I mean, here it's not as critical, but now let's add another core. So let's add a third core with some background low criticality tasks that also relies on shared memory. So you can think of it, it can be a logger, a web server, something like this. We look like this. And we see that workload on core 1 finishes in time, but it takes longer now. And workload on core 0 now misses its deadline. And keep in mind, this wasn't the case when we tested it in isolation. So what do we do here? So
don't caches help mitigate this?
I mean, caches help a little bit. Yeah, they're local to the core, right? But I mean, not everything goes into cache. So if you have some workload that's doesn't have not good temporal constraints, right? It will go outside of the cache and main memory, and that becomes an issue. So what do we do? So in such scenario, for example, for scheduling, so we have to either readjust our worst case execution time analysis of the task, right? Considering the multi-core scenario. But it can be very hard, right? Because it's very hard to predict the condition. Or we need to have a control over the memory bandwidth of some of the other cores to alleviate their pressure on the shared resource, right? For example, if you could limit the core 2 memory accesses, which is not really important core, it's low criticality, that would alleviate the pressure of core 1 and core 0, and thus core 0 wouldn't miss its deadline, and we can predict it much better. So let me demonstrate what it's going to look like. So the solution, which I just said, is to upper limit a core's or task, any target, memory bandwidth. And the obvious way to go is to use some sort of controlled throttling. So, yeah.
Sorry, but so in the network community, this has long been a problem, and they solve it with fair scheduling and what kinds of, right? Why can't we just apply the same kind of techniques?
So I mean, so I'm not really sure about how they do it in network, as I'm more systems person. But here
That works with systems. But like when you have packet contention, you have a local area network, you have a lot of, you have the same kind of problem. One machine might be feeding packets onto the shared local network.
So what's the exact solution?
You need scheduling that is fair, that guarantees that everyone gets similar access to the shared medium or the bus in your case. Or the...
Right, but in real time. So for example, if you want, you can do it for scheduling, yes. But here, what we propose is more finer granularity, first of all. And secondly, if you want to be on a level above scheduling, right? If you're on a hypervisor level and you want to throttle the whole system, right? Then probably.
So you're dealing now with memory transactions that are subject to hardware scheduling in hardware.
Mm-hmm.
You're saying you could change the architecture,
Yeah.
right, to allow arbiter. Yeah, I mean, if you're willing to change the hardware, yeah, you could.
I mean, why haven't they? I mean, it seems like that would have been a natural thing to do.
Yeah, there's not a lot of. So there are some. So here's the thing: a lot of his research has informed what the platform of the future will look like. For example, now ARM is proposing something called MPAM that doesn't really do scheduling. I mean, scheduling is a bit hard to do in memory because
It's so fast.
it's not. But the problem is not enough to decide which transaction goes first. It's really a problem of who is really consuming a lot of the bandwidth in the backlog of things that have already been submitted. And so in the end, it's better to actually kind of like throttle, decide how many things are accepted per unit of time in the memory subsystem. And you can implement custom hardware. What Ivan will show is that you don't actually need to, because essentially what he has is a way to throttle things very fine-grained without having to need custom hardware.
Okay. Yeah. So we're gonna do some sort of control throttling, right? And let me demonstrate you what it is. So to finish our example, let's see if we do that for core 3, which has a low criticality task, and it would look like this. We will let it run sometime. We're gonna halt it. Let it run again. Gonna halt it. And because of this, clearly it's gonna access memory less, and it's gonna improve the predictability of the system overall. And now we can see all tasks finish in time. Right. So we talked about what we want to achieve. Now let's see what's going to be the main pieces of such memory bandwidth regulator. So there are two things to discuss, right? So first, we need to be able to estimate the bandwidth of the target in real time. That's one thing. Secondly, we should be able to enforce the actual control throttling by suspending and resuming the workload of the task or any other target. So since these are the main objectives, let's list what we can do for each of them to achieve. Right. So first, let's start with a real-time bandwidth estimation. So for this, one thing we can do, we can rely on the performance counters. For example, the last level cache misses. Also, we can rely on some custom hardware, some custom memory controller. However, we can rely on the cache coherence trap. And as you might guess by the name of the paper, we're going to talk about it in a bit. Now let's see what we can do for enforcing the regulation. So the obvious thing we can do, we can modify the OS. We can instrument so it's going to deschedule and reschedule back the task that we want to suspend and resume. And the other thing, we can rely on the core's debugging infrastructure, such as core side and ARM, for example, to literally halt the core and resume it later on. So before I demonstrate our work, I just want to give a quick overview of the background works. And so far, there are two major state-of-the-art techniques in this line of work. And namely, they are going to be MemGuard and MemPol. I'm going to briefly introduce them. So first, MemGuard. It's roughly 10 years old. And the idea is simple. So it relies on PMU's ability to interrupt the core once performance counter reaches a certain threshold. And inside the interrupt scheduler, it deschedules the running task. And then it has another periodic interrupt, which is responsible for scheduling the task back. And it's good. However, it has some known limitations. So first of all, it's the interrupt overhead, right? Though it's very small, it quickly accumulates and it becomes a problem eventually at finer granularity. Second, it has some inherent pessimism because interrupt handlers themselves, again, they have some memory footprint, right? But the system can only differentiate the target's memory footprint from the interrupt handler's memory footprint. And again, it's small, but it accumulates over time. Then third, it has a single monitoring dimension, which means that generally only one type of PMU counter can be used. And another one, which is not here, requires less modification. But since MemGuard is kind of already integrated into the kernel, it might not be a big issue at this point. And with all this, it managed to achieve a millisecond regulation in granularity. Another work is MemPol. So MemPol is much younger. So this work is around 1 year old or 2 years maybe now. It relies on PMU counters as well. However, here instead of PMUs generated interrupt, it pulls the counter periodically from some auxiliary on-chip real-time processor. And to halt or resume the workload, it relies on the core's debug infrastructure. And it's actually much better in terms of granularity. You can see it achieves a microsecond regulation granularity, which is like 1,000 times better. But it also has some known limitations. So first of all, control to overshoot. So we don't have control over the bandwidth and the window of time between the PMU poles. So if the target exceeds its desired bandwidth, there is nothing the system can do. And also it lacks awareness of the access location. What it means is that the smallest regulation target in this case will be a single core. We cannot do per memory region regulation. We cannot do per process regulation, only per single core. But yeah.
So for example, if you have multiple memory controllers, you can tell which one is being saturated. So you have to reason on the total bandwidth.
You can also take advantage of this if you know the polling interval. You try to cram in and get it to constantly overshoot and give yourself, percent or 20%.
You can kind of like be more conservative, including the possible overshoot, you're saying?
I'm looking at it from the perspective of an attacker. I'm trying to get my particular.
But another problem with the overshooting issue is that because of this, it also introduces a slow down the whole system.
Right, but again, if I'm trying to get my process to get advantage over all the others,
Oh yeah. You could hack it, sort of like
I can make sure to schedule my computations in such a way that I always overshoot.
Yeah. And you steal more from your.
If you always overshoot, then you're going to be you're still going to be halted for the amount of time you overshoot, right? It's just going to be halted later. That actually might slow you down more.
Yeah, but you can throw off basically the regulation because you go period in activity and then you schedule your things when you know is in between polling intervals,
Right.
and you can cause it to basically cause more often than
I mean, you can do it on purpose.
Yeah, exactly. You can basically maliciously.
Yeah. Right. So let's move on. So if you put MemPol and MemGuard on this slide, they're going to stand here. Right. So they both rely on the PMU, unit to estimate the bandwidth. And for the control frontend, they use a bit different techniques. As I said, it's as instrumentation for MemGuard and the debug infrastructure for MemPol. Now let's see where we stand on this slide. So for bandwidth estimation, we rely on cache coherence trust, and I'm going to talk more in depth about what it is in a second. And for enforcing the regulation, very similar to MemPol, we rely on the core's debug infrastructure. However, we do this little twist, and we're going to talk about it as well. So, since these two are the main components of our system, let's dive deeper into them and see how we use them. And after this, I'm going to demonstrate like the simplified example of how the system works, and then we can have a little demo. Right. So first, let's talk about cache coherence. So what is cache coherence? So generally, on the system on chip, we have a PS cluster. It contains all of the cores and their private L1 caches. Also, there's a last level cache which is shared between all of the cores. There's a cache coherent interconnect and a memory controller. And the idea of the cache coherent interconnect, or as we call it CCI, is to keep last level caches of all the subsystems in a consistent state. So, for example, if the last level cache of the PS cluster cannot find the required cache line, the CCI, in addition to requesting the data from memory, it will also try to what we call pull the data from all the participants of the cache coherence. And turns out in a lot of the systems and chips, FPGA can be made participant in the cache coherent interconnect. And it will look like this. So we would have our UltraScale cluster. And for our example, it's going to contain our MemCoRe regulator module. And in addition to that, it's also going to contain an ACE compliant module. And ACE is a protocol that we use to communicate over the CCI. So we set up our system to allow FPGA to be part of cache coherency. Or in other words, we say that FPGA and the last level cache of the PS cluster are in the same coherency domain. So now it allows us to see all the smooth requests made by the last level cache of PS cluster on the FPGA side. And most important part of the smooth request contains the physical addresses of the requested cache lines. So it might be kind of a lot to digest. So let's walk through a very simplified example of what's gonna happen here. So we have the same setup as before, right? We have the PS cluster, PL cluster, cache coherent interconnect. So assume now that core 0 running a task for which you want to monitor memory access. So first of all, for our monitoring, to be able to understand for which core or task a snoop is made, we need to map this core task to a known physical memory range. And this can be done through a variety of methods, like we can use a partitioning hypervisor, we can use cache coloring, we can use some sort of kernel module, and all of them are well studied and use techniques. And in the implementation of the paper, at least, we decided to go for the kernel module just for simplicity. So now, so let's assume the task on core 0 is mapped to the specific physical address range, and the running task now wants to read some data from memory. So first, the request goes to L1 cache, and it's not found there. Then the request goes to last level cache, and it's not found there. The last level cache sends a request to the cache coherent interconnect, or what we call it, last level cache makes a snoop request over the cache coherent interconnect. So the CCI, at this moment, it does two things simultaneously. So first of all, it makes a request to the main memory for the data, but it can take some time. So in addition to this, it also asks all the participants and for this data. And one of these participants is our ACE compliant module. So once our ACE compliant module receives the snoop request, it also does two things at the same time. So first, it informs the MemCoRe module of the physical address requested. So it informs our MemCoRe IP that the memory access for a specific physical address was made. And in addition to this, it also responds to the CCI with an acknowledgement. And acknowledgement basically means that it has received the snoop, however, it doesn't have the data. So the CCI can take the data from the main memory and forward it back. So eventually, the DDR will come out with the data, and the data will be transmitted back to the task. So now we have allowed our MemCoRe module to monitor a selected target's memory usage in real time, and with basically no overhead, because this exchange here, this particularly happens much faster than access to the memory.
You take the hit on the LLC miss.
I mean, LLC has to be right. The LLC is hit. I mean, there can be contention on LLC, right? I mean, monitor it.
You're adding. You're basically adding. Causing the LLC to have to request this data. So everyone's doing this. Presumably, you reduce your performance.
No, I mean the thing is, I mean, we're not like disabling our LLC or in any sense. I mean, if there is a data powered in LLC, we don't need to struggle with memory access, because what we are doing here, we're doing memory access throttling, right? If the thing is found in LLC, it will be found in LLC, it will never go to memory.
Also, you're relying on the core to actually make that request, right? You're to that specific address.
Yeah, it's like a normal load or store. It's how often.
Right. Yeah. So first,
Right, but you're introducing it into the software, into the.
I mean, you can just monitor those addresses that you know they're gonna be requested for applications, right?
These are supposed to be specifically outside of the typical memory.
So no, it's just saying, I think that what's confusing there is that range, where what Ivan said very quickly, is that basically this task, when imagine allocates its heap or its stack, all the physical memory is always allocated from a specific range. So this is just normal memory the task is using.
And this is outside of that range.
No, it's inside.
Oh, it isn't.
So the only thing that is needed is that we know which task is associated to which range, so that when we see a physical address, we can account it to the right task.
So you're not actually instrumenting.
No. Exactly. This is doing its own business, and this is one of the loads or stores that the task is using to do its computation.
So why would there be a miss on the LLC then?
So just to clarify, sometimes there is a miss on LLC, right? So what we are doing here, again, so we're trying to regulate the memory access, and we don't modify the application in any way. But in normal application usage, not everything found in cache, right?
That's correct.
It's not found in cache, it will go to memory.
So
And
you're
that's
monitoring the LLC misses as a proxy for computation.
basically, yeah.
As a proxy for the bandwidth consumed by that task in the DDR subsystem.
It means that if I have something that has very good temporal,
Exactly. Don't need to regulate it because it's not
you won't regulate.
correct. And you don't want it because essentially it's not creating any contention, or at least it's not exacerbating the contention in the memory subsystem. Yeah. And
It's interesting.
Yeah, okay, yeah. So just to finish this, so now at this moment, from the perspective of our MemCoRe IP, we know everything, right? We know everything in computer bandwidth. We know the physical address where the access is made, so we can correlate it with the target. We know the amount of memory that was accessed, that equal to the cache line size, right? And we continuously monitoring it, so we can compute the bandwidth. Right. So this is for the monitoring part and for bandwidth estimation. So the second part, as we talked, was the control throttling, right? Well, the actual way to enforce the regulation. So for this, we rely on the debug infrastructure. And here's how we use it. So again, maybe it's quite a lot to digest, but let's try. So again, so we have the PS cluster. It contains cores. And in ARM, there's a core science system, which is just their umbrella term for all their debug subsystems. And each core is connected to a debug module. And this debug module has capabilities to halt and resume the core. Each debug module is connected to what's called a CTI, which is a cross-trigger interconnect. And here, the details and specifics of this are not important at all. But what's important here is that you can make an exit transactions to the CTI to instruct the correlating debug module to take some action, right? So to either halt or resume the core. And exi is just a memory mapped interface. Basically, it means we can write to some unknown memory address for the CTI to take action. Each CTI, in addition to that, is connected to a cross-trigger matrix, which is connected to another CTI, wires, literal wires, which we call triggers as well, to the FPGA. And yeah, so the picture might be overwhelming, but what it means is this: in simple terms, from FPGA perspective, there are two ways we can actually instruct the core to take action. So one of these ways we can do for exi, so for literal memory transaction, we just write it to a known address. And another way we can do it through these triggers. And these triggers are just wires connected to the FPGA, so we can raise them high and low to be taken. So there are two routes which you can do. So yeah, first of all, it's an exi route, and on average, this takes around 420 nanoseconds for the regulation to take place, either halt or resume, doesn't matter. And another route is going to be the trigger route. And the trigger route can also be used to halt or resume cores. However, it has some caveats. So first of all, each trigger has to be pre-configured to a specific core and specific action. And the number of triggers is limited. Second, if you choose to use it for resumption, the trigger signal has to be followed by a specific exit transaction anyway. But this is actually not required for halting. So this is only required for resuming the core. And for timing, it's a bit better than exi. So on average, it takes around 100 nanoseconds for the halt regulation to take place. So because of this, the way we decided to use it is the following. So due to the limitation of the triggers, and we decided to use the triggers to halt the cores. So, and the idea behind this was to suspend the workload immediately. So to prevent overshooting as much as we can. And we decided to use Xi to resume the course. And here the delay is not as crucial. So because the core needs some time to accumulate bandwidth. So this is the sort of connectivity path that we use. Yeah.
Did you also measure how much perturbance does the halting and resuming the core cost? Because like you have some states that you have, the application was in currently, and now it has to resume back, and that state might not be there.
Right. So I mean, we measured in terms of timings for the DVBS and different benchmarks. So usually for halting, as I said, for triggers, it takes around 100 nanoseconds. And same, but for resuming, we couldn't measure. So for resuming, there is no feedback on resumption actually, because when you halt, there is a feedback, so you can get a feedback when it actually completed. So you can measure it. For resuming, there is no feedback, but based on some metrics, we think it's around the same.
What's nice about this is that when you use this debug interface to stop a core, you don't actually send an interrupt. So it really freezing its pipeline, and the cache remains clean. And basically, the only thing that impacts this timing is the time it takes for it to flush anything in the pipeline and basically finish any outstanding writes, if I remember.
It's finished the writes and then.
Yeah.
Question.
Just a simple question. Here we are pinning tasks to the course, right? Because otherwise we need to fight with the scheduler that will be allocating the same task.
The course, yeah. So we know on what course. Yeah.
When you halt it and it finishes its write, it's finishing its writes to its local cache, right? The L1.
It's
Or
finishing
to-
any outstanding.
Finishing outstanding writing. So it probably, in terms of the cache, I don't know honestly, but I assume it probably goes to last level cache, maybe even to map. I don't know.
Oh,
Maybe.
No.
Even some,
Okay,
yeah, like getting all the acknowledgements for the outstanding rights,
but this could also be a problem to say.
like a barrier. Yeah, what you say?
No, that could take a while if you.
Yeah. That's why.
That does take a while, yeah. But on average, it's around 100 nanoseconds. It can be a bit more. So in the paper, we have the exact metrics. It might go up to, if I remember correctly, 250, something like this. But on average, it's around 100 nanoseconds.
Does this provide any like giant local perturbance when you halt it? Say you have a application that has like a lot of outstanding writes, like it has to immediately write back right after you halt it. Do you have any applications that stress this like?
Oh wait, no, we're not cleaning the cache. We're not cleaning the
But you're
cache.
writing back. Right?
No, so you know how in the pipeline you have, these are non-blocking caches, right? So when you send for example, you have a miss, right?
Yeah.
The misses could be outstanding.
Yeah.
So that means that the corresponding instruction has not been retired yet because it's waiting for data
Mhm.
to be served from the
Oh,
memory.
okay.
So it has not been completed. The same for a store. Until you get the right acknowledgement, the store is kind of pending and it will be retired only after.
Okay.
I think this is what I mean by has to flush the pipeline, everything needs to be retired.
Mhm.
Because otherwise, this is meant for debug, right? You can't really debug a core if its state is still changing the moment you stop for
Yeah,
debug.
Understood.
It will declare I'm in debug mode when this pipeline is completely clean, but not the cache. The cache can be dirty. That's allowed.
Yeah, so one thing to mention, so the triggers for the twist that we mentioned are different from MemPol. So MemPol they just use Xi. But yeah, so now we know that the two main components of the regulator. So we can monitor the bandwidth, we can enforce the regulation. So now let's talk about the actual regulation logic that we use. And we can substitute it for a different policy, but that's what we use currently. So what we use is called a token bucket regulation model. And the model is actually very straightforward and it's very common in networking actually. So the idea is this: each regulation target is associated with a token bucket where tokens represent available cache lines. And it has three simple rules to follow. Three rules. So rule one, if a bucket is not empty, the target is allowed to run. So the terminology here is going to be the current budget is greater than the target the bucket is associated with is running. Second rule, buckets are periodically refilled with fresh tokens. And the terminology here related to this is going to be the replenishment value, with how much we refill it. And then replenishment period is how often we do it. And the final rule is bucket cannot exceed a predefined token limit. And here we have the maximum budget of the bucket. So we cannot refill more than the maximum budget. So now let's just run
The rule for what happens when it's empty, right?
it on, right? So the first rule, right? If the bucket is not empty,
Presumably, if it is empty.
it is empty stuff.
Well, though that's not
Exactly.
logically.
Complete. But
Right. So now let's
Guess it should be an if and only.
If and only.
if and only. Right. Okay. So let's just go through a simple example. So let's say we have 4 targets, which can be 4 cores or 4 different tasks, but let's say just 4 cores. And we want them to maintain this bandwidth in memory. So 100 megabytes for target 1, 300 for target 0, 300 for target 1, 500 for 2, 1000 megabytes for target 3. So then here we have to pick the replenishment period. It's up to us which one we pick. Here, let's say we pick 10 microseconds. Now we have to pick the replenishment value and maximum budget. And here we're going to keep them the same. You can keep them different if you want some specific regulations, but in general, there is no real need for them to be different. I don't see a scenario for that. And to compute the replenishment value and maximum budget, we apply this formula, which is, if you look at it, it makes a lot of sense, right? So it takes in replenishment, it takes in the bandwidth, it takes in the cache line size, which is given in 64 bytes in our systems. It takes in the replenishment period, which we just need. And all that known here is the replenishment value. That's some unit conversions, but at the end we can get the replenishment value, and we're going to set the maximum budget to the same number. So after we apply this formula, we can compute the corresponding replenishment value. So now let's see how the system would behave. So at time 0, all the targets are full. So all their buckets are full. Then the system runs the excess memory, and let's say at time 4, then obviously the number of tokens in each bucket splits. Then eventually, at time 5, the bucket for target 1 becomes 0. We immediately notice this on FPGA side because we continuously monitoring this. So we immediately issue halt regulation. System runs, time 7, see target 1 is halted. Target 0 reaches the bucket of 0. So we immediately issue a halt regulation. System runs, then at time 9, both target 0 are halted. They still have some valid tokens in their buckets. And eventually we reach the time 10, which is our replenishment period. So we replenish all of them with the corresponding replenishment values, and obviously capped by the maximum budget. And because now these two are in greater than 0, the value for their bucket is greater than 0, we issue resume immediately.
So you could end up a situation where all 4 targets have 0 and are doing nothing.
Correct.
You could presumably use, resources, but no one's doing anything.
Absolutely right. And what I present. However, in paper, we also talk about a global regulation. I don't have this in presentation, but there's also like a global regulation overall, which has some global tokens available for everybody in the situation you described.
What do you mean global tokens for everybody that anyone can just grab?
Yeah, so like a global regulation policy on top of fair target regulation policy.
Yeah, but then you have to worry about attention. I'm not quite sure how you do the global.
We can go over it at some
You
point.
can go over it, but not yet.
But it's interesting question. I think.
I mean, because I can imagine there'd be workloads where you will actually deplete all 4 of them.
Yeah, no, that's possible. Yeah.
Yeah, in fact, I mean, there are actually, so let me put it this way, right? What are budgets that make sense? In the end, the budgets that make sense are the ones that, if you take the sum, it's no more, but also no less than what the DRAM can sustain, right? Because that's the quota you want to allocate. However, what can happen sometimes is that, so that's, you split it up. What happens sometimes is somebody has run out of budget, right? But actually, overall, the consumption is way below that total value. So in that case, what the paper already does, I believe, says, okay, you know what? I should normally regulate you, but actually right now, the DRAM is underutilized, so I let you go because the global allocation is still satisfied.
Another addition on top of this, I mean, remember from the first example, not everything you want to regulate. So maybe this 4 run out, yes, but there's something else running on the system that we don't regulate at all, and let's keep it running. So these just don't take, you leave it there, memory access, but not some other targets. So that's also a possible scenario, right? We want all of them to be, if they use all their budget, it's fine. That's also possible, yeah. Right, so that was a simple example. So now let's just before we conclude, let's talk about implementation and evaluation. Look at some graphs.
In fact, sorry, just to get back to it, I think it's likely to happen because when you use up your budget, that means that someone else is gonna get more time. And they're gonna exhaust their budget faster. So it's likely that you'll actually end up with these kinds of states.
I agree.
So we implemented it on this board, which is Xilinx Zynq UltraScale Plus platform, and more specifically, this is a CCU 102 board. What interests among its specifications, what interests us is that it has 4 application processor units, so whatever we showed before. Each of them has a private L1 cache, they have a shared L2 cache, last level cache, and they have a core side debugging infrastructure. It has a sizable onboard FPGA, and the last level cache in FPGA can be made here. Right, so now let's go to evaluation. So first of all, let's take a look at the FPGA resource utilization, which is kind of important. And you see the percentage of the lookup tables and flip-flops is very small, both less than 1%. And what it means is that our system can be integrated with any other FPGA program, FPGA software you might have, right? So it doesn't necessarily have to occupy the entirety of the FPGA. And all of the XI connections, that it uses, it just basically monitors them, except one XI, which it writes to. So you can also share them as well. So you can integrate it with any FPGA you have, which is very good. And now let's actually see the graphs. So first, let's just see general comparison. We have MemPol. So this is an example of MemPol with a polling period of 6.25 microseconds. So now just for a fair comparison, alongside we have a MemCoRe periodic. So here I didn't really probably describe this completely, but in the normal version, as you might have guessed already, we halt immediately when there's an overshoot, right? In this version, we don't do it. This version, we let it run until the replenishment period, and then we decide if we want to halt. So it's basically whatever MemPol does. And this we just did for a comparison, and you can see they behave almost identical, which is exactly
Why are there 0 gaps in both?
It's very dense.
But there's like, there are periods where it goes down to 0.
here.
Yeah, here and there.
Alright.
Maybe just not use the memory at this point, right? So this is the so this was covered with the monitoring program, right? That monitors the memory access. It's not.
So you don't think it's an artifact of the?
I think it's also because it's regulating it, no?
Yeah, that's a question.
It's either, but I think honestly to 0. It might not be because it's just not using memory at this point, or it has some very good temporal constraint at this point.
What applications?
This is just bandwidth. It initially does some setup, so maybe this is like a setup part.
Oh, yeah, that big gap there, yes.
Yeah.
Yeah, that's probably just.
from the setup because we don't see it. We see it a little bit here. Right. So then you can see it behaves. It's very basically exactly as MemPol, which is a good sign. However, even the periodic version, which doesn't do the asynchronous, what we call asynchronous halting, which it does halt in not only the replenishment periods, it can do much better in terms of the period, right? Even here, we can achieve a 2.2 microsecond period. The main reason is because first of all, the regulation logic in FPGA literally takes 2 FPGA clock cycles. We don't use PMU, and halting is done through triggers. So this is very good. But now let's take a look at the real deal. So here's the real deal. So here's our macro system with a synchronous pulse and the replenishment period of 6.25 microseconds. And you can see it controls the bandwidth very well. We can get the replenishment period even lower to around 1 microsecond. And you can see how precisely that makes the set point. So this was more of synthetic benchmarks. So now let's look more realistic benchmarks, which is the San Diego Vision Benchmark Suite, SDVBS. So if you take a look here, on top we have the unregulated version, like the red line, which is set point. It just not really means control. Then we have the deregulated under MemPol, and then we have it regulated under our system, MemCoRe. You can see how well it obeys regulation to MemPol.
So the x-axis is iteration, so
Yeah, x-axis is just time. And y-axis is the bandwidth.
So it when it's done with all the jobs, that's blank. So in other words,
Yeah, when it's done.
so you're able to finish faster than.
Exactly. And we're able to finish faster in some things.
Yeah.
With the same set point.
Need the same set point, be able to finish faster.
That's interesting.
It's less overhead.
It's considerably faster.
Yeah.
Yeah, the idea behind this,
It's basically right in between the two.
the idea behind this just so yeah, because what MemPol does, right? It has this period where it falls, right? So MemPol has this period where it falls, and let's say the program uses here a lot of memory, and it overshoots by a lot. So now when it holds it, it has to hold it for the entire period, or maybe two. In our system, when we do this, the system uses bandwidth, and then when it exceeds the set point, when it exceeds the budget, when the budget goes to zero, we immediately halt it until the next replenishment period. And then the next replenishment period, we replenish it, and it goes back into the positive range, so now it can run again. Yeah. So because of this, we achieve a much better in terms of slowdown, much less slowdown compared to MemPol. Yeah, I mean, it's not for some. I mean, we always better. And some of them is more pronounced, like here. Some of them is less.
The one that use more memory.
The one that more memory.
Which makes sense.
So yeah, so just for a slowdown, we have another comparison of slowdowns here. And yeah, it's basically similar to what you saw before, right? So for disparity, much better in slowdown. So the yellow here is MemPol. Some of them is. Right, so just some conclusions here. So first of all, the pros of our system. So first of all, it solves the overshooting problem. There's basically no overshoot. It allows fair memory region regulation. It has a negligible overhead. It has a very small FPGA footprint, so you can incorporate it with any other FPGA routine. And it's easy to implement token bucket model, which is also extendable, right? As I said, there are possibilities of global regulations, or maybe some other way to extend it. So the logic is very simple. But it has some limitations, of course, as well. So first of all, it requires physical address to target mapping. So that's one thing. And second, we can only monitor read operations so far. So we can only do the enforcement on the read operations. So we cannot monitor writes. Right. And the granularity, we claim that we achieve a nanosecond regulation granularity. And this claim comes from two things. So first of all, we can hold a core within 100 nanoseconds after detecting a budget overshoot. That's one thing. And second one, in the replenishment period, we can actually set it as low as 0.6 or 0.7 microsecond, and it will work. So with this, we claim a nanosecond regulation granularity.
Well, it's microsecond.
100.
It's hundreds of nanoseconds.
Seconds.
No, 0.7.
Otherwise known as microsecond.
0.7 microseconds, 700 nanoseconds.
Yeah, I mean the thing is in anything before you cannot go below microsecond. We are able to go below microsecond.
It's some
Yeah,
microsecond.
100 nanosecond regulation.
Another
Nanosecond regulation suggests at the nanosecond you.
1 nanosecond.
Yeah.
I think another is literally the signal to halt is literally 2 nanoseconds. It just takes the system response as
yeah, reaction
So
time
the thing is, yeah, so the halt is very, very quickly. I want to emphasize it's very quickly compared to MemPol, right? It's 100 nanosecond for a halt usually. The worst was around 250. So the halt is quick. Right. Yeah, so that's all. If you're interested, please read our paper. We're going to show a little demo now. Yeah. It's not very exciting, but I'll show you.
Just a quick question. What was the MemCoRe like FPGA implementation? How fast was that part running at?
Oh, the regulation logic is like 2 clock cycles, 1 clock cycle.
frequency.
The frequency of this.
The frequency 100 megahertz.
Okay. Could you pump it up more?
You can, yeah,
Okay.
you can pump it to 300. It doesn't really matter. 100 is fine. Right. Let me show. Let me try demo here. Let's see if it's gonna work.
sub nanosecond.
So what's nice, I don't know how familiar you are with the way DRAM subsystems are organized, right? Internally, you have different banks, right?
Yeah.
Typically, those map to different ranges of physical addresses, and each of them can work in parallel. So one thing that we have in the roadmap is actually that by looking at the physical address, you can be bank aware. So instead of talking about the saturation bandwidth for the entire memory controller, you can be aware of which bank is being saturated.
But the banks can operate in parallel, but don't they have a?
Yes, there's this the arbiter and the data and address bus. But that the bandwidth of that is actually typically over provisioned compared to the actual bank machinery. But we'll see. I guess that's so we're gonna have essentially we have 4 banks, we have 5 limits, 1 per bank plus the global arbiter. That's fine. You have an address, a command bus, and a data bus.
That's the provision.
Yeah, I mean, it's really limited by the law.
Yeah. If I connect to the server,
Why the banks are limited in latency, latency of that.
So the memory is the content.
Yeah. The raw part, the raw side.
That's like kind of
Here, the problem is all transactions are always cache line size. So you can really, this is what we do in TAB. Try to
that's what I was gonna say. This is more than its wheels.
Yeah.
Of accelerating.
in that case, you need to know and control somewhere the access path.
How do you test the policies? So you have the global and local policy.
Mhm.
How do you test the policy so that you know that it's doing really well versus doing really bad?
That's a good question. So,
I think so, yeah. On the ZCU? Yeah, yeah, it's probably PDU one.
you working on your
We
terminal?
were the first to look at this stuff.
I don't think we still see the.
I think your thing is broke. Doesn't let me restart.
This is why you should always have like a video recording.
Yeah.
No, it's not a video recording. So we have a server where
Yeah.
we have all the boards connected to the server, and
Yeah.
he's our sysadmin.
Oh.
He manages it. He doesn't restart. But he'll figure it out.
I always tell my students, any live demo you do, always have a backup.
Yeah, yes.
Because live demos 50% of the time go.
All is fair.
50%, you're very optimistic.
Well,
50% is good.
Even Bill Gates, remember when he was demoing Windows
Yeah.
and crashed the entire audience.
Think with the demos of Surface, right?
That was the famous one, the blue screen of that was being Windows 2000.
Yeah, that was Windows 2000. Someone lost their job over that.
Yeah. And then there was also the flop of the Surface when the Surface just froze.
Yeah.
Just a real
There's a
deal.
50% chance of it failing.
You could also do the software.
It's a real deal. This is shit. The truth.
How do you do the software?
It's fine. I mean, we have 5 weeks. Since we get money.
So what would the demo show?
Yeah.
Just run and show it running.
What's wrong with this?
No, this is on the board. I want to reset.
Yes.
Right, so let me just show the demo. It's kind of
Okay. We gotta switch the share here.
Wait, can you on that one? It just says connection close.
Oh, I think there was shenanigans from the guy beach. So you do the.
okay. So the idea is
But
we're gonna use different cores here because I cannot show you the core with them.
Sorry.
So
Question back here, sorry.
Can you just increase the font size? Command plus. Thank you.
I think it just increased the terminal.
This is one of the things that it works on my computer.
Yeah, that's correct, yeah.
It just increased the terminal. I think.
This is bigger.
So the idea is this. So we have our bandwidth. Bandwidth physical here means that it is the bandwidth where it maps all of the application to non-physical address range. Then here, of course, 0 specify what core we are running it, and memory just specify how much memory the bandwidth application uses. So the bandwidth is just a simple application that goes through memory buffer. It keeps it with the cache line size, so it will always meet the cache. And if you run it to core 1, which is non-regulated, you're going to get a 751 megabytes per second. So that's a non-regulated version, no regulation. Now that here on core 0, we have a regulation set to 150 megabytes. If you run it for 0 now.
Ivan,
Have a regular.
I can reset you.
Fine.
Okay.
Right. So we can also try changing the regulation. Let's see if that's going to work. So it's going to be. So we can change the period. Let's give it to this. Let's give it like 1.5 microsecond. So it's our replacement period. And let's set the bandwidth on core 0 to be 250 now. And the rest, let's just. So the monitoring, they set it to coherence. And right, so if you run it now, let's hope it's gonna work. We get 250, right? It's working.
Yeah, so
Right, so this is the demo.
Yeah.
Actually, that's all of it. Now it's going to do the demo is running the SDVBS, but then this SDVBS wouldn't get this like the bandwidth used. You have to upload it with the table. But yeah, so that's basically it. Thank you very much for attendance.